Alright, this is a video for Precalculus, Section 1-1, Part 2. So we're looking at two major concepts. We are looking at solving graphically, which we've kind of touched on sometimes before, and grapher failure and hidden behavior. So let's start with something we should already know, and that is the zero factor property, also known as the zero product property. It says that a product of real numbers is zero if and only if at least one of the factors in the product is zero. So if we have a times b is equal to 0, then that is true if and only if a is 0 or b is 0, and by or I mean both could also be 0. But that applies to any number of products. If I have a times b times c, I'll put the c here, then the same thing, I just keep going with this. Okay, so this is an alternate example 6. There is another video for example 6 that is on your Moodle. It's one of the videos that are at the bottom of the week. It's not a link, it's an actual embedded video. And it may take a little while to load, but you can watch that one if you want. So this is a little different than the one that they did. The one they did was in the book. So solving an equation algebraically. So we're not doing graphing, we're doing algebra. Find all real numbers x for which 2x cubed equals negative 3x squared plus 2x. Well, let's get this equal to 0, shall we? If we get this equal to 0, we get 2x cubed plus 3x squared minus 2x equals 0. The first thing you should notice is that you have a GCF of x. So if we take that out, we get 2x squared plus 3x minus 2 is equal to 0. Already I know one answer. Whenever we take an x out, that means x of 0 would make this true, right? If I plug a 0 into all of these, it would be true. This all would equal 0. So then that leaves us with a quadratic. We can check to see if it's factorable. Two numbers that multiply to make negative 4. Remember there's an a, so I multiply a times c, and then add to make 3. And that exists. That's 4 and negative 1. So you may remember various methods from your previous classes on how to factor this. The way that I do it, after I multiply a times c and I get this and I find my two numbers, is I pretend like I'm just going to go x plus 4 times x minus 1, although I know that's not the answer. But then what I do is I divide these two numbers by the a value, which is 2. And sometimes it simplifies, like right here it'll simplify to be 2, and sometimes it doesn't. And if it doesn't, the denominator has to go in front. And so it gives me the answer of x times x plus 2 times 2x minus 1. It's a weird little method, and you're gonna have to prove it for yourself for why it works, but it just works. And you could check that it works. If you were to FOIL these last two things out, you would see that you would get the original 2x squared plus 3x minus 2. Okay, now, so we already got one answer of x is equal to 0. The other answer is going to be negative 2. And this answer over here is going to be x is 1/2. So those are my three solutions. Some terminology that was in the book. This is really important. Make sure to get this down. I took this straight from your book. These are various sort of, make this a little bigger because it's that important. Okay, these are sort of the definitions of words we use kind of interchangeably a lot because they all kind of mean the same thing, but they're slightly different. If a is a real number that solves the equation f of x equals 0, then these three statements are equivalent. So the three statements that are equivalent are The number a is a root, we use this word root, of the equation f of x is equal to 0. Another word for that is solution. So a root is another word for a solution to an equation that is equal to 0, where we have an equal to 0 involved. The second one, a is a 0 of the function y equals f of x. So that's another one. If I have f of x equals y, so this is some function, and I let this y be 0, I get zeros. Now, sometimes those zeros are x-intercepts, sometimes they're not. It depends on if it's a real number or not. Well, actually, we specified it was a real number. So if they're not real, then they're not zeros. Okay, so the number a is an x-intercept of the graph. So this is the visual way of saying it, right? If we have a function and we graph it, those are the x-intercepts. They're also the values of x here, whatever the x is. I'll call this x1, x2, x3. Those values are the roots slash zeros slash x-intercepts. They're all kind of the same thing. So that's why we can use graphing as a way of solving. So for example, we have this equation, x squared equals 3x minus 1. We're comparing methods here. Again, this is an alternate example to the one that's in your book. You can look at the one in your book, and then you can compare it to this one. So we can solve this fairly easily. This is a quadratic. Let's use the quadratic formula. So I'm going to set it equal to 0. Do the quadratic formula. So negative b, negative 3, negative 3, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 1, all over 2 times 1. Okay, so then we get 3 plus or minus the square root of 9 minus 4 over 2. So 3 plus or minus the square root of 5 over 2. Now, this is what's known as the exact answer. But we can get decimals for this. If we were to calculate this out, we'd have to do 3 plus the square root of 5 divided by 2. And we'd probably have to round that, so we'd approximate that. So taking 3, we'd have to figure out what the square root of 5 is. So the square root of 5 is 2.23. As soon as you start rounding, 2.236, so 2.24. As soon as you start rounding, you don't have an exact answer anymore. And we really want to have exact answers as much as possible. Okay, so we can add 3 to that. We get 5.24, and we divide by 2 to the whole thing. And this gives us approximately 2.618, so we could say 2.62. Now, I actually didn't use this number, this 2.24. I wrote it down, but in a calculator, I figured out what the square root of 5 is. It gave me a long decimal. I didn't delete that and then start over with 2.24. I always use the exact number if possible. And then I added 3 to that, and then I divided 2 to that, and at no point did I ever round. I just let the calculator do the next step. So then we can do the same thing with 3 minus the square root of 5 over 2. So again, we take the square root of 5. I just start all over fresh. Then I'm doing 3 minus it. So I could just make that answer negative and then add 3 to it, because I'm not subtracting 3 from the square root of 5. So in my calculator, I'm not doing this, because that's not the same thing. I'm going to make it a negative square root of 5, and then I'm going to add 3, because that's equivalent to this. Then I'm going to divide by 2. So the square root of 5, make my previous answer negative. Then I'm going to add 3, and then I'm going to divide by 2. And I get approximately, because I am rounding, 0.38. Okay, so the other method that we can use is by graphing. All right, so let's open up our graphing program. Either if you have a graphing calculator, I don't know what this is. Ignore that. Okay, I'm going to try and make my window a little bigger for you guys so that you can see. Okay, so let's open up Desmos or whatever graphing program that you guys have. And we type in this function. Or we're typing in y equals x squared minus 3x plus 1. We're replacing the 0 with y. So y equals x squared minus 3x plus 1, right? Yes, okay. And then we're looking for the x-intercepts, which are here, 0.382, and here, 0.2 or 2.618. And then if I go back and I look at my answers, just move this back over. That is pretty much exactly what I got. I didn't round as far as they did. I did 2 decimals, but that's pretty much it. Okay, let's look at one more thing, and that is hidden behavior behind a graphing program. Now, I think a lot of you know, especially with the more computerized graphing programs like Desmos, that you can zoom in and zoom out and in order to find things, right? Just what you see is not necessarily what you get. Sometimes you think it didn't graph it, but then you realize if you zoom way, way, way out, oh, there it is. It's way up there. You have to find it sometimes. So that is what's called hidden behavior. Right here. Okay, so sometimes they say the viewing window will be too large, obscuring details of the graph. So sometimes it's just saying you have to zoom in and zoom out before you can see exactly what's going on. And sometimes the graphers don't exactly do what they're supposed to. And that's grapher failure. And that happens in weird situations such as where you have asymptotes or just the domain issues and things like that. So here's the graph of y equals 3 divided by 2x minus 5. This is a hyperbola. You have an x in the denominator. It's a hyperbola. It looks like this, right? You got your branches. Now, in a regular old graphing calculator, you'll notice they drew this line. Now, that is not part of the graph. That is the asymptote, except the grapher doesn't really see that as an asymptote. It doesn't graph asymptotes. It's trying to connect dots that shouldn't be connected. It wants to connect things. But if you look at the table, you can see there's an error here because we can't put in 2.5. If we put in 2.5 in the denominator here, you will get 3 divided by 0 because this is 5 minus 5. So anytime a grapher has a line like that, and you know it shouldn't really be graphing anything, ignore it. All right. Now in Desmos, it may or may not do something like that. Let's just graph that same thing and see what happens. Graphing calculators and Desmos are not the same thing. Okay, so you could see in this program we did not get that funny line. Okay. But there's other situations that this one could essentially do. let me give you this for example. I think this is actually one of your homework problems, so pay close attention. If you take x to the 200th power, it looks really weird. Okay, it almost looks like things are vertical or that things are completely flat, but we should know better. This is not going to be a straight line on the sides. Otherwise, that would not be a function. But if we zoomed in a lot, let's go over to this edge. You can see it's curving. There's a curve. And although it looks like it's hitting 1 the whole way, if we follow it, if we trace it, look at the numbers. It's not hitting 1. It's getting so close to 1. And then we hit 1 eventually. Right about here, we hit 1. And then it gets bigger. But it's still very, 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 very close to 1. But at no point is the x value repeating. So that's something you want to pay attention to. Now these are going to 0. But here's the problem. This isn't actually the one I wanted to show you. I want you to then take this to the power, and I'm going to use parentheses here, 1 over 200. So I have x to the 200 equals to the 1/200th power. So if you think about that, the 200 and the 1 over 200 will multiply, and you'll just get 1. Let me get rid of those. So if you look at the graph that we get, it looks like an absolute value. Now, there's definitely reasons for why the left-hand side here is positive, and that's because if you take a negative number to an even power, it will become positive. So you'll never get a negative out of this. So it's kind of like an absolute value in this sense. But if you look at this, it kind of looks like over here you just have y equals x on this side. But if you zoom in, and I do mean zoom in, you notice something funky happening. What the heck is going on here? Well, here's what's happening. If you take a really tiny number, like this is 0.05, so if we take like this right here, which is like a really, really tiny number, and you take it to the 200th power, because that's what it's doing, it will be a number so small that this computer, this program, thinks you have 0. If you take, in a calculator, any of these numbers, so like 0.00 or 8 or whatever it was, any of these numbers, if you take that to the 200th power in a regular old calculator, it will tell you, I think that's 0, because it's so small. And so what the grapher is doing is it's just estimating. It's saying, okay, x to the 200th power at this point is 0, and then I take that to the 1 over 200th power, and well, that's 0. So it's 0, right? Not exactly, but it doesn't know any better. There's only so much power a program like this can have in order to give an accurate answer. So it says it's 0, but it's not really. So we can't depend 100% on what a calculator tells us, even one as cool as this. So that's just your warning for that. As we go through this course and we're using this, there is something we need to pay attention to for this program, and that's it's gonna make mistakes. Okay, so that's it for this video. All right.